Good morning, boys and girls, and welcome back to the second day of the fundamental theorem of calculus. Part 1. Remember, we kind of switched the two parts of the fundamental theorem. The second part, I believe, we kind of used more, so I want to cover that first. And now we'll talk about the first part of the fundamental theorem of calculus through this little activity here, and then we'll kind of introduce it. Okay? But I want to start here with our area function. Remember, an area function is a function that will give the area under a curve. So here we have the area function, a of x, is the integral from 2 to x of f of t dt. Okay? And if we look to the left over here, we have that function f. This kind of confuses us sometimes in the beginning. Just watch out here. It's called f of x over here, right? But f of x, f of t, those are the same things. Just different variables, x versus t. The reason we got to switch to a t over in our area function here is because we're already saying that x is like the place we're going to stop for our area, right? This is the area under the curve from 2 to x. And so we kind of got to change this variable and kind of just make it, we call it like a dummy variable. All right? But what this is saying, again, what our area function is representing is the area from 2 to x. Okay? So that is that, this area here underneath the curve. Okay? That's what that area function is representing. As this x value travels in or out depending on what x is. Okay, I guess we should say just so long as, x is greater than or equal to 2. As long as that is true, then we are okay with this thing. Then we have an area function. All right, so before we jump into the fundamental theorem, we're just going to kind of do some quick review practice stuff. Let's first just go and calculate a of 2. So if we want to calculate a of 2, that is the integral from 2 to, again, with that a of x means I'm just going to plug that in for x. So the integral from 2 to 2 of f of t dt. And we have talked about with our integral rules, if we're doing an integral from someplace to someplace and it's the same value, then that is going to be 0. If that ending value is right on this same exact line here, if that was my x, then there is no area under the curve, and therefore that's why that answer is 0. All right? That one's easy peasy. A little bit of review. Next, we're going to find a of 5. So a of 5 would be the integral from 2 to 5 of f of t dt. And so again, what that is representing is the area under the curve from 2, instead of x now, to 5. Okay? And now if we wanted to go and find this, we could do this a few ways. Since we talked about the fundamental theorem of calculus yesterday, I guess we could actually plug in the function and integrate it. Or what I'm going to do today, we're going to kind of go back again a step. This represents the area under the curve, so I'm just going to find the area of that little shaded region. That shaded region is a trapezoid, so the area would be 1/2 the base 1 plus base 2 times the height, where this would be base 1 on this side, right, and this would be base 2 over here, and the height would be along the bottom. All right? Or another way to write this would be 1/2 base 1 would be f of 2, and base 2 would be f of 5, and the height would be 5 minus 2, right? You would take that big value, whatever it is, and subtract our starting area, and, that would give me the height of the rectangle. So in this case, the height would be 3. If we actually go and plug in numbers now, 1/2 f of 2 is 7. If I plug 2 into our formula up here, 2 times 2 is 4, plus 3 is 7. F of 5 is 13, and 5 minus 2 is 3. So I get 1/2 of 7 1/2 of 7 plus 13 times 3. 7 plus 13 is 20, times 3 is 60, and half of that is 30. So there we go. That is that answer right there. Like I said, just to kind of double check, not just for funsies, all right? If I just did this through evaluating using the second part of the fundamental theorem of calculus, the integral 2 to 5 of 2x plus 3 dx, we should get the same exact answer. Okay? So if I integrate this, add 1 to the exponent, divide by the new exponent, so this just becomes x squared plus 3x, evaluate from 2 to 5, or this becomes, well, I should not just start evaluating. This becomes 5 squared plus 3 times 5 minus 2 squared plus 3 times 2. Or this becomes 25 plus 15 is 40. 2 squared is 4, plus 6 is 10. So I get 40 minus 10, or I get 30. Again, same answer either way you do is just kind of what I'm trying to show there. Just remember that this indicates the area under the curve. I guess that's what I'm trying to do. And this is our area function. And, all right, there we go. Okay, I want to come back to this, again, this area function. Again, brand new kind of clean setup here. And I'm going to play around with this again, just slightly differently, though, this time. We talked about how this is an area function that represents the area under the curve right here, right? Of this curve right here from 2 to some value such that x is greater than or equal to 2. All right, let's see. I want to write, we found the area at 5 in the previous problem. I want to come back. I want to find an expression for the area for any value under x. Okay, so if we, again, continue to use this idea that this is a trapezoid and we're going to try to find the area here, we can kind of go and similarly, just the way we found the area before, 1/2 base 1 plus base 2 times the height, I can do this all in terms of x so that I have a function a of x, exactly the same as that one, but as a polynomial, all right? So this would be 1/2. Base 1 is still going to be f of 2. Base 2, though, would become now f of x, because we don't know where we're stopping. And my height would become, again, wherever we're at, minus 2. That endpoint, last time we went 5 minus 2, my height would now become x minus 2. And so now I can go ahead and I can plug in here 1/2, f of 2 is still 7, plus f of x is 2x plus 3. And then times x minus 2, and we can go 1/2. This is 2x plus 10 times x minus 2. I'm going to take half of x minus 10, so that's x plus 5 times x minus 2, or x squared plus 3x minus 10 would be the function, the polynomial function, that would give me the same height, same area as this right here. Like, all this stuff is the same way, just different ways of writing all this stuff right here. Now, here's what I want to kind of play around with a little bit, and this is going to lead us to our second part of the fundamental theorem of calculus is, excuse me, if I go and play around with this, if I compare these things a little bit, if I take the derivative of a prime, if I find a prime of x, if I take the derivative of a, that's kind of hard to do. We don't know how to deal with that in the integral here. But that's what the second part of the fundamental theorem of calculus is going to deal with. But I can take the derivative of this polynomial over here. That would be 2x plus 3. And what we're going to try to point out here, what I'm trying to point out is, when you take the derivative of an integral, since these things were all equal, the derivative of this integral, d dx, of the integral of 2 to x of f of t dt, I hate how my stuff all runs together, that is going to equal 2x plus 3. Okay? Or, if we look at this, the derivative of this integral is the same thing as f of x, right? F of x is 2x plus 3. The derivative is 2x plus 3. Prove that through a polynomial right here. And so, when you take the derivative of an integral, this basically is leading us to the the first part of the fundamental theorem of calculus is really all I'm going to do is I'm going to take whatever is up here and I plug it in right there. So that was f of t and it became f of x. F of x is 2x plus 3. So that is my derivative. It seems kind of weird and confusing. And I feel like we always make this more difficult than it needs to be. But the first part of this fundamental theorem of calculus should be real easy. It's just plugging in. Let me show you some examples. I guess real quickly here, let me officially give us the fundamental theorem of calculus part 1. And that is if you take the derivative again of this area function, or if you take the derivative of this integral with respect to x, again, as we're taking the derivative with respect to x, all you're going to do is you're going to plug in the variable. It can be from any constant, a. A can be any constant, doesn't matter. You're just going to plug in the x into this function, whatever it is. And then you're just going to get f of x. Okay? That's what this first part of the fundamental theorem of calculus says. All right, now let's do an example. So if I want to take the derivative of this integral here, a couple important things that, to use this part of the fundamental theorem of calculus. It's got to be from a constant. The bottom part has to be a constant, and we're going to go from a constant to x, or to a function times, you'll see, but you've got to have an x up here. Okay? And then you'll generally have like t's down here. But when I take this derivative, all we are going to do is we are going to plug in whatever is up here. So the derivative of this would be e, and I'm going to plug in wherever there's a t, I'm going to plug in x. E to the x. Done. That's it. That easy. That is the derivative. Okay? That's why I say I really don't think this is that crazy or that hard. Let's do another one. Okay, here we go, number 2. I'm going to take the derivative of this integral right here. Now we said important things when we do this. It has to be from a number to x, not x to a number. So the first thing I would have to do here is I would have to rewrite this and change it. And again, the way we do that with our integral properties and make that a negative. And then I can switch my limits. But it has to go from a constant to the variable or the function. And now when you take the derivatives, that all you're going to do is you're going to go plug in. So I got to keep my negative out in front. And I'm just going to plug in the square root of x to the 4th plus 1. That would be the derivative. These should be real easy problems, I'm going to say, when you do this. Okay? Should be super quick. Let's just plug it in. That's all you got to think about it as. Okay, this might be about as hard as they get. Maybe a little bit harder, but not much. Where you got to watch out and pay attention is when you are plugging in something than just an x. If you're plugging in an entire function, you got to be a little bit careful. The rule is going to stay the same. I'm still just going to go plug it in. Now I know over here, this confuses us sometimes here, this dp over p squared. Just remember dp is your differential. If you don't like this, you could rewrite this as 1 over p squared dp. That might be, a different way of seeing this. A different way of writing that, but those two things are the same thing. So, we said all you got to do when you take the derivative of this, though, all you're going to do is you're going to plug in. So this would become 1 over x cubed squared. 1 over p squared. I plug in for the p, whatever it is there. The tricky part of the thing you have to remember with this is, because we're taking the derivative, if you have an inside, you've got to do chain rule. So I would now need to multiply that by the derivative of the inside, or the derivative of that thing that I just plugged in, and so I'd have to multiply by 3x squared. So this answer would be 3x squared over x to the 6th, or this would be 3 over x to the 4th. And that would be our derivative. So just remember chain rule when that comes in. If you have something other than x, take the derivative of the part that's up on top. Okay? Always got to go from a constant to the function or to the x. All right, one more little tricky thing to show you, and it's really not that bad, and we are done for today. Okay, here we go. Last one of our craziness, and you'll see, again, this still really is not that bad, but this probably is about as bad as it gets here. I've got to take, I forgot the derivative. I need to take the derivative of this integral from negative 2x to x to cosine 2t dt. Our issue here is we said it's got to go from a constant to an x. I've got 2 x's here. Oh no, what do I do? Again, we're going to use our integral properties, and so what I'm going to do is I'm going to split this up, and I'm going to go from negative 2x to, you can make up anything. It doesn't matter what that constant is. Cosine 2t dt plus the integral from 0 to x of cosine 2t dt. But we said, hey, if you split the up, as long as these things are the same, that is equivalent to the integral that's up on top there. And now I need to flip this one around so that, again, I have the constants on the bottom. This one's ready to go. This one is not. So I did my negative and flipped things around, and now I'm ready to take the derivative and just plug in. When you plug in negative cosine 2 times t, or negative 2x here, just don't forget you need to use chain rule for something other than x. So I have to multiply by negative 2. If it's an x, I can just plug in. And then if I simplify, I end up with this answer right here. And that's it, boys and girls. We are done for today. Good luck.